All right, let's talk a little bit about disintegration series, radioactive decay, and we'll move on to some radioactive dating and applications of nuclear chemistry. The disintegration series starts with usually a natural series. In our case, we'll talk about the uranium-238, 235, and thorium-232s. You can see that they all start with substances with pretty long half-lives, and then you see a lot of radioactive things that would appear in rocks based on that. And you could continue down the series and look more towards the bottom. You can see that sometimes there's some branching. You don't certainly have to memorize this, but it's in your textbook. You can see that it goes through a lot of different things. And so if we want a data sample, we have to look at this complex combination of isotopes with different radioactive substances in the rock. And so it's sometimes a little bit more complicated than we make out. So let's look at radioactive dating. One of those would be, for example, radiocarbon dating. It's pretty much a one-step one, so it's a good one for us to look at. A lot of times it's used to look at things that were alive at some point. So nitrogen-14 becomes ionized by radiation in the upper atmosphere, absorbs a neutron, then becomes a proton. And so the nitrogen ejects that proton, becomes a carbon-14 instead of a carbon-12. That is radioactive, and we can use it to date things because the carbon-14 reacts with oxygen to form CO2, and it becomes incorporated in the plant life and then moves up the food chain. The half-life is 5,730 years. It's a beta emitter going back to nitrogen-14. Usually they say after 10 half-lives it's gone. A lot of times carbon-14 is good to about 50,000 years or so, they say. Much more than that, I wouldn't bank on it. I've even seen on supposedly scientific programs where they've got this thing like a Tyrannosaurus, and they're saying they're dating it by carbon-14. That obviously is not going to work. And they have not done their research. So just keep that in mind if you're looking at that. So if we got a piece of wood and it's got 33% of its original carbon-14 activity, so using our half-life of 5,730 years, we know that at the final amount, it's got 33% of its activity. So initially, it would have 100% of its activity. Essentially, we're wanting to find the time it took for it to decay that much. And so we can use our first order kinetics. So let's look at the problem. We're going to start with the kinetics equation, ln of A equals negative KT plus ln of A0, which this chapter more conveniently arranges it this way, particularly if you're wanting to solve for T. So T would equal 1 over K times ln of A0 divided by A. Before I can get to calculating that, I need to get from half-life to K. So K was equal to ln of 2 divided by the half-life, or ln of 2 divided by 5,730 years. So ln of 2 divided by 5,730, K, we're going to put that in scientific notation, is 1.21 times 10 to the negative fourth years to the minus 1 power. So now we can plug and chug. It's a small number, but that's okay. It's going to go with a long half-life. And so we got 100% divided by 33%. And so 100 divided by 33 is going to be 3.03, etc. We're going to take the natural log of that number. And then essentially we're dividing by 1.21 times 10 to the negative fourth. So that time is going to be 9.90 going to 3 sig figs times 10 to the third years. So not quite 10,000 years, but close. And so that would have given us a date for how old that piece of wood was. That is, the last time it was alive. You don't know how long the tree grew, but from the time it died to the time this measurement was taken, you know how long that time was. That's what we're trying to say. There are certainly other methods for dating. For example, potassium argon or uranium to lead. For example, and igneous rocks contain a lot of potassium. So we can look at the electron captured to argon with a half-life of 1.3 times 10 to the ninth years. And it works for dating some older objects. But the calculations would work the same as the previous example. Uranium lead relies on uranium going to thorium 234. This is the 238 decay series. It's a very long half-life. So how do you go about looking at all those complex decays from the decay series? Because it was quite the list. Sometimes people treat it like one reaction and do an approximation. If you're really serious about getting a good number, you've got to look at all those decays simultaneously. That requires a little bit more math than we're going to be able to do in this class, so we'll stick to the approximation. If you've done some more advanced math, really it requires solving a set of simultaneous differential equations, which is above the math level of the class we're trying to teach here. Take more of a nuclear class with a higher math requirement, and we could certainly chat about that. Talking about transmutation, that is, if we have a nuclear reactor or some sort of collider or accelerator, we can collide particles, cause the nuclei to fuse, and produce different isotope elements that may not naturally occur. We can certainly produce elements and isotopes that do occur, but we can make some that don't naturally occur, and a lot of those elements down in the 100s and following never naturally occurred. They've only been made in a lab through some of these transmutation type reactions. The rules for balancing these reactions still hold with what we said in the previous video. You could have a cyclotron, for example. We have a high energy beam which passes through, but it's caused by these D-shaped electrodes alternating, causing the particle to spin and spin and spin and spin faster and faster and faster until it's allowed to escape. And it strikes a target and if it strikes it at just the right energy and everything, so they'll generally fuse together, usually by emitting some smaller particle as a result. And many of the new elements have been synthesized in that fashion. Here are some bombardments that could happen. Molybdenum-96 bombarded with deuterium, forming technetium-97, and it kicks out a neutron. If you notice, it does balance. 96 plus 2 is 98, 97 plus 1 is 98, 43, 42 plus 1 is 43. So, hey, the balancing rule still works. Bismuth 209 gets bombarded with alpha particles. You form astatine 210, and it kicks out 3 neutrons. Notice the 3 out front means there's 3 of those. Thorium 230, you hit it with a proton, you get 3 neutrons, and you get Pa 228. Neutrons are great for bombardment because that you don't really have to accelerate them to overcome the Coulombic repulsion between two nuclei. You have two nuclei, they're positively charged. They don't like to come together because of the proton-proton repulsion, so you have to accelerate them, but not too much. And you got to get it just right, because if it's too much, you may get shattering, or they may bounce off of one another without fusing. If it's not enough, you don't overcome the repulsion. So it has to be just so they'll meet and potentially fuse. Neutrons don't have to work that way because they're uncharged and therefore don't have to be accelerated. Neutrons to have a large kinetic energy are called fast neutrons. The slower neutrons or thermal neutrons have their excess energy decreased by collisions with moderators, say in a nuclear reactor. They can be hydrogen, deuterium, hydrogen atoms, and paraffin. Whatever is going to slow it down to where they're more likely to be captured rather than bounce off. For example, you can bombard Mercury with a neutron, you get Mercury 201, but it gives you a gamma ray. Lithium-6 is forward with a neutron, and you make tritium, which is the radioactive isotope of hydrogen that does not naturally occur. We live in South Carolina, so there was a big story quite a few years back where there was tritium in the Savannah River and everybody was in panic mode. And it kicks out an alpha particle. Nuclear fission, usually that's a function of large atoms will undergo fission, small atoms do not, at least in general. These atoms will split to atoms of intermediate masses and emit one or more neutrons usually. Some fission reactions are spontaneous, others require activation by neutron bombardment, as is the case with nuclear power. Enormous amount of energies can be released in these fissions, which we then can use for our benefit. Uranium-235, if you bombard it with a neutron, you temporarily get a uranium-236, but it splits up any of several different ways, and that's not really an all-inclusive list. But you get a large amount of energy, and you get neutrons that can then cause other fission reactions that keeps the energy going. So if you have a nuclear reactor and your nuclear power plant, you can keep that energy going and continually produce power. Synergetically favorable as long as the atomic number is greater than 80. This is the binding energy curve. You can see that it maxes out in the mass number around 50 plus or minus, and then decreases. So you can see that these large atoms like uranium down here at this part of the curve can split into things more in this range and produce something that's more stable, so they do. Things that have low atomic weight and low atomic number will tend to fuse, like your hydrogen. You generally need high temperatures, and that's the predominant feature going on in our sun. Still focusing on the fissions, however, the biggest thing if you got a nuclear power plant is the core meltdown caused by these fission reactions. That is, you've got to take away enough heat, or the heat becomes trapped and starts melting your fuel rods, the pressure of any steam produced in your boiler, and then that can blow apart and hurl radioactive material into the atmosphere. 3 Mile Island back in Pennsylvania, back in the late 70s, irradiated a good part of eastern Pennsylvania. Still lawsuits going on. Chernobyl, which is now in the Ukraine, it was part of the Soviet Union back then, back in the 80s. One of the reactors at least partially melted down, and there's parts of some of those Baltic states like Lithuania or Belarus that have large uninhabitable areas, and some of that's just starting to come back. But some areas are still too radioactive for them to let people live in. After the tsunami hit Japan somewhat recently, the reactors melted down because the tidal wave caused by the tsunami or the earthquake knocked out even the backup systems to keep the reactors cooled down, and they fully melted down. And they had trouble stopping it and venting a lot of the radioactive water into the Pacific, which wasn't good. Light water reactors tend to use water as a coolant. One, because hey, it's cheap, and it's the coolant and the moderators of the fuel rods are sitting in the water, which then can be heated and turned to steam turbines for your power plant. And radium-235 oxide can be fuel pellets or plutonium. Moderator serves to, again, slow those neutrons down, make sure you don't get too many reactions. You can use graphite or water or heavy water, which has one or more deuteriums instead of just a plain old hydrogen atom. The control rods are usually made out of boron, which is an efficient neutron absorber, which reduces the number of neutron collisions. So it's designed not to reach a critical mass where you would have a nice mushroom-shaped cloud where your power plant used to be. These are specifically designed not to do that. We do have to worry about the radioactivity. There has been a little bit more emphasis on nuclear power plants because of the push to have power plants that don't have so many greenhouse gases emitted. And while they don't generally emit greenhouse gases in terms of carbon dioxide, the only carbon dioxide would be in the construction of the plant, perhaps. But you do have to worry about what to do with that radioactive waste that comes from the reactor, and so it's not necessarily green. The cooling systems remove heat from the nuclear reactor. A lot of times we use water in commercial reactors because we're going to use it to turn a steam turbine to produce the electricity that is transmitted, but it can be helium or even liquid sodium and probably a couple other things. You're going to need shielding, usually a mixture of lead and concrete. Those big dome-shaped type bunkers that are around it are generally made out of a combination of lead and concrete. You can see the basic setup. You've got the reactor assembly here. You got water that circulates. The water that's in the reactor never goes outside, but that water is pumped through a steam generator or a broiler, where that water heats the water in the broiler, then produces steam. You turn a steam turbine, which produces electricity, and then you usually have a pond or a lake or a river running water through a condenser that allows that water in the broiler to recondense and come back to the steam generator assembly. But the water that's in the reactor or whatever fluids in the reactor never hits the outside. So, because it's generally in direct contact with the material. Now, if we focus on fusion instead of fission, that's taking lighter nuclei and fusing them together to form heavy nuclei. If you remember, fission has two S's, fusion has one S, and so that's a good way to keep them straight, as a lot of students confuse them. That's the primarily energy source in a star, and it's usually deuterium and tritium forming an alpha particle plus a neutron plus lots of energy. But usually you need high temperatures and high energy required to get this kick started. Fusion can produce elements up to iron, typically, which are at the peak of that nuclear binding energy. It's generally not energetically favorable after that. Thermonuclear hydrogen bombs have been in existence since the 50s and does involve a little bit of fusion. It can be a possibility if you can overcome the energy barriers, but fusions generally require high energies, which require lots of energies. That's why you see movies and they're talking about cold fusion. That is, they've come up with some alternate mechanism where that's fictitious, but eliminates the need for these extremely high temperatures, which is what makes fusion an unreasonable energy source at the present time. If you want to win a Nobel Prize, figure out how to make that work. some exist around the world, but they're not any sustainable fusion reactions. It could be a potential energy source in the future, but who knows? They'd really have to make that work. And so let's look at some potential transmutation type reactions. And it doesn't matter whether you know what these elements are. Sometimes you may not. But the point is you can balance a transmutation very much like any of your other decays. The balancing principles are the same. And then we just want to take a moment to make sure that we can balance them. So let's go to the paper. I've copied these over. So if we got 246 and we want to add 12, so 246 plus 12, we got 258 on the top. We got 4 neutrons, so 4 times 1 is 4. So we're going to subtract 4. And so that top number is going to be 254. And then 96 plus 6 is 102 total on this side. I don't have any atomic number, so we're going to go with 102. Then what we have to do is we look on the periodic table to find element 102. Nobelium 102. So we're going to write NO. And does it matter that you really know what that element is? Not necessarily for the purposes of balancing these things, as long as you can look on the periodic chart and get the proper symbol. So next one, 230 plus 1 is 231 total. 2 times 4 is 8. So we're going to say 231 minus 8 is 223. And then 90 plus 1 is 91. We got 2 of those, so 4 over there so far. So we're going to say 91 minus 4 is 87. Right now we just need to come back and figure out what element 87 was. And there it is, francium, or francium if you're in a more British area. Regardless, FR. And so that would be a balanced reaction.